We need a framework in which we can understand the accuracy of an algorithm. So here's a good framework. Suppose we have a mathematical function t whose inputs come from a norm vector space V and whose outputs are in a norm vector space W. So this is the actual mathematical function. And by the way, although t and v and w are both norm vector spaces, I'm not assuming that t is a homomorphism or a linear transformation. It's just some function. And t tilde also goes from v to w. And it's an algorithm. So the point is that, for instance, suppose V is the space of square matrices, and W is also the space of square matrices, and the function T is take a matrix, and apply row reduction to obtain its reduced row echelon form. So the input is a matrix, the output is the reduced row echelon form of that matrix, with a pure real number answer. That's fine. But of course, you can never actually compute that with arbitrary accuracy. T tilde, therefore, would be something like this. You take a square matrix. The entries, which are real numbers, are somehow rounded off to some accuracy, maybe 52 binary digits if their numbers close to 1, for example. And you look in the first column and find a good pivot. You use it to clear the rest of the first column. You look in the second column, find a pivot, swap some rows to put that pivot in the appropriate spot, do some division and subtraction to clear the other things in the second row, and second column, and so on. And so in the end, you obtain something that is the reduced row echelon form matrix, but it's not quite exactly the reduced row echelon form matrix you would hope for, because there have been all these steps along the way. First of all, the rounding of the original numbers, and then every step of arithmetic has some error built into it. So t tilde, applying Gaussian elimination on rounded decimal numbers, on floating point numbers essentially, is an algorithm that is somewhat like the function of take a matrix and output its reduced row echelon form. And the question is, how good is it? That's an example we'll come back to. For now, we just want to discuss the notion of stability. So there are two notions that we want to keep track of. The first is stability. So we say t tilde is stable. And this is sometimes called forward stable. In the following situation. For all x, so you take an input x, which lives in V. There exists some x tilde, which is nearby, and we'll define nearby in just a moment, such that if you look at the outputs of the exact function applied to the nearby input and the computed algorithm applied to the original input, I want these to be close. And by close, I mean the following. I want this to be the actual answer of the nearby point. So this relative error should be on the order of less than or equal to the machine error. So I'll use epsilon for machine error. And we haven't said where x tilde lives yet. X tilde is also relatively close to x. So these norms are the norms in the norm vector spaces V and W as appropriate. So that's our definition of stability. The picture is something like this. We have an input x, and we can compute that input. Using the algorithm, we can get an output. So here's the algorithm t tilde, and we obtain something that I'll maybe call y tilde. Now, nearby y tilde, there's some y, which is the actual answer for some input x tilde using the actual mathematical function t. So the goal is that we want to make sure that if we're defining t tilde, which is supposed to represent t, that you can get nearby inputs. You can get nearby outputs using nearby inputs. In other words, for every input to the algorithm, there's a nearby input where the outputs are also close. And they're close in a relative sense. We want to talk about relative accuracy here because, again, we're going to be using floating point numbers. So the notion of accuracy for floating point number, because of its structure as a fraction and an exponent, is essentially a logarithmic accuracy. So we want to look at the fractional accuracy of the inputs and outputs. So we want small relative error. That's our goal on both ends. We also have a notion called backward stability. So again, we're considering the algorithm t tilde for a mathematical function t from v to w. So the idea here is quite simple, actually. So it's going to be stronger than forward stability, but it actually ends up being easier to work with in many situations. So the idea is that for any input x, there's some nearby input x tilde, such that this very simple thing is true. The exact mathematical function of the approximate input is equal to the approximate algorithm of the original input. And of course, we want the two inputs to be close together. So we want x tilde minus x over norm x to be on the order of machine error. So the picture here is very simple. You've got an input x and an input x tilde, and the input x gives an output y using the algorithm t tilde, actually let's say output y tilde, and the input x gives an output, the input x tilde gives an output y using the actual mathematical function t, and the two outputs are equal, not even close, but just equal, whereas the inputs are nearby. So in the example of forward stability, both the inputs and the outputs are approximate. But for backward stability, the outputs are identical. So Trefetherman-Bell has a very pithy statement for this. It says that an algorithm is called backward stable if it gives the exact correct answer to almost the right question. Whereas an algorithm is stable if it gives approximately the right answer to approximately the right question. Both forward and backward stability are related to the ideas of condition numbers. A condition number is a way of measuring how sensitive a function is to variations on the input. It's sort of like the Lipschitz constant you might study for a function, or it's really also the continuity and the notion of what's the ratio of the epsilons to the deltas when you have your epsilon delta definition of continuity. So let's define this for a function. If we have a function, say f, say from v to w, and again, this can be an algorithm or it could be a formal mathematical function. It doesn't really matter. This is just a formal definition. And so if we have an input, let's call the input x, and it has got a variation of delta x, and x, say, goes to y, and let's define delta y to be exactly what you might expect. So this is f of x plus delta x minus f of x. So again, this is the same thing you study in calculus, right? So you've got an input x, you've got a nearby input x plus delta x. This input has output y, and you've got some function here. Here's y plus delta y, and we're just drawing the triangle with sides delta x and delta y. The classic secant triangle for a function. Okay, so what we're going to do is we're going to define the condition number. This is actually the absolute condition number. This is the following idea. We take the difference quotient, delta y over delta x. Now this is essentially the norm of what you'd normally call the derivative difference quotient, right? So you take the, if this didn't have norms, this would be the classic derivative. But we're going to take norms, so we're looking at the ratio. And now we're going to take the supremum as the size delta x is less than or equal to delta. Now this maybe doesn't make so much sense in this picture, right? But what it does, well, I guess what it's doing is it's saying, suppose you fix a radius delta in the x direction which you want to study. And we're going to consider, among all delta x's inside that radius, what's the maximum slope that you see appearing here. So it's sort of what's the worst case if you take all the different secant lines, what's the worst case slope, the steepest slope, positive or negative, if you look at all the different secant lines within some radius delta. And then we're going to take the limit as delta goes to 0. So this is very closely related to the idea of the derivative, but we're being a little more precise about it. We're not just taking the limit, we're taking the limit of the supremum in some range. This is called kappa tilde. Or kappa hat, I should say. Kappa hat of f at x. So again, it's very similar to a derivative. The derivative would not have the absolute values, and the derivative would just be a limit, not a limit of a supremum in a range. But it's a tightly related idea. Now, when we're dealing with floating point numbers, we care about the relative error, because in the floating point number scheme, because we have a ratio of a certain length for any given exponent, that ratio of the minimum variation of the fraction versus the ones position is the thing that's constant, not the absolute error. So we need a relative notion of condition number. And so here we go. This is the relative condition number. So this will be called kappa. And again, it's of f from v to w. And we'll again say that we have delta y and delta x. So we've got x, and we've got delta x variation, and this goes to y, which yields a variation of delta y, which is f of x plus delta x minus f of x. So delta y over delta x is your standard difference quotient. Okay, so this is the condition number. Kappa it's going to be the ratio of the relative errors. So it's delta y divided by y. That's the relative error of the output, and that divided by the relative error of the input. So it's just like the quotient we were looking at before, the difference quotient, but now we're doing a relative difference quotient. And we play the same game. We take the supremum over all delta x's within some domain delta, and then we take the limit as that domain becomes smaller and smaller. So we're asking for smaller and smaller neighborhoods. Within that neighborhood, what's the worst possible ratio of the relative errors? Now, this is sort of interesting because, of course, thinking about the derivative, let's suppose that the derivative of f is given by a matrix J, the Jacobian. So that means that delta y is approximately J delta x. That's in fact the definition of the derivative, right? It's the best linear approximation of the function for a multivariable function. So this is essentially our definition of the derivative J, and that means two things. First of all, our original condition number, absolute condition number k hat, is really just, well, again, if the function's continuous and differentiable near x, then that whole limit of supremum business is really just a plain old limit in supremum. And as the delta x goes to 0, we can say that that is the absolute value of the Jacobian. Now, when I say absolute value, what I actually mean is the matrix norm. I shouldn't have said absolute value. The matrix norm of the Jacobian. So both v and w have their own norms. Of course, J is acting on the tangent space of v at x to the tangent, and it's going to the tangent space of w at y, which, being vector spaces, those are both copies of v and w, so we can interpret J as a matrix from v to w. It's got a matrix norm coming from those induced norms. And so usually, for example, this is a 2-2 norm or an infinity-infinity norm or something like that. Now, that's the relative condition, the absolute condition number. We have a similar formula for the relative condition number. So here we go. We've got delta y over delta x in this fraction here. All right, so rewrite the fraction as one big fraction with 4 parts. And we see that, in fact, we have a numerator here, which is the absolute condition number divided by y over x. So this is the matrix norm of the Jacobian divided by the norm of y over the norm of x. So again, we see that the notion of the derivative, the Jacobian, is tightly related to the idea of the condition number, either absolute or relative. And in particular, basically, what the condition number does, whether it's absolute or relative, it's combining two ideas. So condition number combines derivatives and matrix norms. And so what we're measuring is the matrix norm of the derivative in either an absolute or a relative sense. And that tells us, in a very clear way, how sensitive the function f is to its different inputs. So our goal now is to use condition numbers to analyze the stability of algorithms for different functions.